Um, so we did the problems on simple interest. We had a little bit of simple interest on the quiz. But actually, if you are earning interest, especially from a bank, you're probably earning it as compound interest. Very rarely do banks compute interest as simple interest. So the simple interest is really more of kind of an introduction to this idea of interest and getting you reminded about how simple interest works a little bit. But compound interest is much more likely to happen. So the first thing we're going to do here is actually watch a quick video that just gives kind of an overview of what it means to have compound interest. We've talked about this a little bit before, but it just gives you a quick overview again. Oh, except this isn't gonna like, hang on a second. Oh, there it is. Every time I plug in my projector, my sound changes.
Kia ora and welcome to the Reserve Bank's podcast explaining compound interest. Compound interest is a pretty powerful financial concept, but not everyone understands how it works. An easy way to think of compound interest is the interest you earn on interest. Here's an example. Jack and Kitty are thinking about saving for a rainy day. They might save for their first house, head off on an exotic overseas holiday, or put money away for their retirement. Kitty's the organised one. She decides to put $1,000 into a savings account, which will earn 5% interest each year. Look at what happens to Kitty's savings balance. In the first year, Kitty's $1,000 deposit earns $50 in interest. So, by the end of the year, she's got $1,050. Kitty also earns interest in the second year too, but this time she started with $1,050 in the account. So, she earns interest on the full $1,050. That means the initial interest is compounded, and she earns $52.50 in interest in the second year. The benefit of compound interest may not seem very large to start with, but as you'll see, compound interest can make a big difference over time. Kitty continues to leave her money in the account each year, and it continues to earn interest. 40 years later, she'll have more than $7,000 in the savings account, and most of that's been earned through interest on interest. Jack isn't as disciplined as Kitty, and he has his mind on other things. He starts by depositing $1,000 into an account, and just like Kitty, it also earns 5% interest each year. But unlike Kitty, Jack spends the interest he earns each year. 40 years later, Jack's still got $1,000 in his savings account. His initial deposit has earned interest in that time, but unlike Kitty, he hasn't benefited from that interest compounding each year. That's the benefit of compound interest. The longer you save without spending the interest, the more you benefit. And the benefits accelerate the longer you save. Of course, if Jack and Kitty were able to regularly squirrel away more savings into their accounts, an even larger sum of money would benefit from compound interest. And don't forget, compound interest also applies to debt too, and certainly not in a good way. The longer you leave debt without paying interest, the more interest it accumulates, and the bigger the debt burden becomes. So to recap, compound interest is a bit like supercharging your savings, because not only do you earn interest on the money you deposit, but you also earn interest on the interest you earn too. And the longer you save, the more you benefit from compound interest.
So I think this is the most compelling part about compound interest. Compound interest is a type of exponential equation. Usually, it is the time that is the variable, and the time is up in the exponent spot. So we get this exponential function kind of curve to it. But notice what's causing the curve. If you notice here, each of these little bars has a gray section and a pink section. The gray section represents the $1,000 that Kitty actually put into the account to start with. The pink represents all the interest she's earned from that. So when you get down the road to 40 years, we had one more here, don't we? Is it going to show me? No. Here at 35, we're at $4,516 in this account. It says by the time we get to 40 years, we're all the way up to $7,040 in the account. Only 1,000 of that is still Kitty's money that she put in the first place. So over $6,000 of what's in that account was interest. It was the money she made on that $1,000 she started with. That's what happens with compound interest. That's what makes compound interest the more beneficial way to go than simple interest. Okay? It's also why you need to give yourself time when you're talking about investment. Okay? The longer you can let your money sit, the more interest you're going to earn. You'll notice here in the first few years, like in 5 years, $276 is all she really earned in interest. Right? Maybe that doesn't seem like much in 5 years. And that's one of the things that we should recognize about exponential functions. Because of the way it curves, if you are, let me actually write it down here. Oh, one of these is working and one of these isn't. And then I keep setting them down beside each other and I don't know which one works. Let's try this one. There we go. All right, so if you're talking about an exponential curve of any kind, it always starts off increasing pretty slowly, right? So the difference from here to here, from year to year, doesn't seem like that much. But then there's always that point where you kind of hit the curve and things start to take off. So you have to be able to sort of wait things out until you hit the curve. And once you sort of make that curve and get around that corner, then the difference from here to the next year is much more significant. So now your increase from year to year is pretty substantial. And so when we're talking about anything dealing with compound interest, if it's an investment where you're trying to make money, time is your friend. The longer you can let the money sit, the more money you're going to be able to make. Because the more interest that's going to get added in so that the next year you're earning interest on not only what you deposited, but also any of your previous interest. Now, as they said, the flip side of that is that if you're the one who owes the money in a compound interest kind of situation, time is not your friend. The longer it takes you to pay that off, the more money you're going to have to pay above and beyond what you actually borrowed. So in a loan kind of situation where you're trying to pay the money back, you want to keep your time short. But in an investment situation where you're trying to earn money, you want to try to keep that money there for as long as you possibly can, because that's going to see more and more growth and more increase in growth, right? It's going to start growing faster and faster and faster for you than what it maybe did the first 5-10 years. Okay, and then as I showed at the end, if you can actually be adding to this, so not just put in a lump sum and let it sit there, but if you can actually put in some money and then add to that money. So see how their gray part is getting a little bit bigger each time? So that means they're actually adding a little bit to their account. That's going to cause this growth to happen even faster for you. So there's going to be even more growth. You're going to make even more money in interest if you can be adding a little bit to it. And it doesn't really take very much. And so one of the things we're going to talk about when we talk about planning for retirement, and one of the reasons why I include that chapter, even though you're all, 17, 18 years old and you're like, Mrs. Gordon, 65 is so far down the road. Like, what are you talking about? Why do we have to talk about retirement? Because as soon as you get a job, and especially any kind of a stable full-time job, you need to be looking into saving for retirement. Because the amount of money you can make in 40 years, from the time you're 25 to the time you're 65, as compared to waiting until you're like 45 and then trying to make money in 20 years' time, it is a lot harder to make the same kind of money in 20 years that you could make in 40 years, and it doesn't take nearly as much to start with of your own money to end up with the kind of growth and the kind of money you want for retirement. So you have to think about this stuff early. You can't wait until you're kind of old to worry about when you really get old. You have to start thinking about it when you're young if you really want to take advantage of how compound interest works. And almost all investments, whether you're talking about a simple savings account, whether you're talking about a mutual fund, anything like that, almost any kind of investment you would make these days to try to earn money is going to be a compound interest kind of situation. So you need the time to really take advantage of it.
And when you say like adding a little to it every single time so you get more interest in the long term, so when you say adding a little bit, like how little does it take?
It really doesn't take that much. Okay. And it also depends on how often you do it. So like if you're planning on at the end of every year you add a bit more to your account, like if it's, as an example, Mr. Gordon and I have some different, not just savings accounts, but also like mutual funds and that kind of thing. Different investments that we have for the purpose of saving for retirement, right? Well, we only go back and talk to the guy who manages that for us every summer. So for us, maybe in those accounts, like once a year, we may decide to add a little bit more to that account, right?
Yeah.
So if you're doing it on a once a year basis, we maybe need to add a little bit more because we're only doing it once a year. If, on the other hand, you were actually in the States, nearby, whatever type of account you had, maybe even just a savings account. But if you could decide that every month when you get paid, you're going to take $25 and put it into that savings account and swear not to touch it. You're just going to leave it there. So maybe you start with $500 or something, graduation money, people gave you gifts, put in $500 graduation money. But every year now from your job, you're just going to add $25 more. Even that seemingly small amount every month can have huge impact on how much interest you end up earning, especially if you then let it sit for 30, 40 years.
Yeah.
And just keep doing that for 30, 40 years. And hopefully, you get to a point where you get a better paying job and you can put a little more into it, but even something as small as $25 a month, I mean, really, over a year, you're talking about $300 that you've put away.
Yeah.
Earn interest on that over the next 20, 30, 40 years. That can make a significant difference.
Makes sense. Thank you.
Okay, and so that's why we're actually, I'm hoping, going to do a little activity when we get to that chapter that shows you kind of the difference of putting in a little bit of money early versus trying to put in a lot of money later, and how that works out. And you might be surprised by the results. But that'll be a little further down the line. So right now, the biggest thing I want you to get from this lesson on compound interest is the idea that time is what makes it work. Being able to leave your money, leave your investment over time, that's what's going to really earn you a lot of interest. And in essence, free money, right? Like, you didn't do anything for it other than let the bank use your deposit that you put in there in the first place, and they pay you for it. Okay? And even with mutual funds, a lot of times what's happening is you're investing in that company or in that package of companies. It's so they can use your money. So they can develop, they can grow, they can build, whatever the case is. They use your money, they pay you a little bit of interest back. And at the end of a certain amount of time, you can get all of that money back. But if you really want to make the money, you've got to be able to do it over a long period of time. Starting when you're 50 isn't going to earn you much. Starting when you're 25, it's going to make you a lot more. Okay? All right, so pretty much what we're going to do today is we're going to take a look at a little bit of vocabulary and make sure we know what we're talking about. And then we're going to do a couple of problems with compound interest, kind of as a review. You've seen this before. We've done it some in Algebra 2. We even did a little bit of it in Algebra 1. So we're just going to kind of review it a little bit, refresh your memory on how to use it. And then we're going to talk about something that you probably have not seen before, which is the idea of an annual percentage yield. What that means, and why we want to know how to use that. So let's start with a little bit of vocabulary. So we're starting out here with the idea of compound interest. Which of those three definitions would you say describes what compound interest is? Number two? Everybody agree with number two? Does that sound right? Okay. So it's interest that's earned on money that you've deposited along with any previous interest you've earned. That's the idea of compounding, getting that previous interest added in, so next time that interest is figured, it's part of it. Okay? When you do compounding, you can do them for different periods of time. So obviously, annual compounding is calculating the interest every year. So at the end of each year, they kind of stop. They calculate what the new amount is, they add that much into your account, and now that sits there for the next year until they decide to calculate it again. Semi-annually means what? Half a year. Semi and bi, those two prefixes, seem to be the two that will get students mixed up. So a semi-annual means half annual, half year. That's every 6 months. A biannual means every 2 years. And I think what messes us up is we know that bi means 2. And so when we see biannual, we're not sure if it means every 2 years or if it means twice a year. But that's actually semi-annual. Okay, so semi-annual is twice a year, every half year, every 6 months. Biannual would mean every 2 years, and sometimes you do see that come up. So just make sure you keep those two straight. Quarterly is also very common. How often would a quarterly compounding happen? 4 times a year. So how often would it happen? Every 3 months. Yep. So if you take a 12-month year, divide it by 4, every 3 months is when your compounding would take place then. Daily compounding is calculating interest so that it is paid daily. Usually we assume that daily means 365 days. If for some reason they are specifically talking about a leap year and they want you to use 366, they will specifically say so in the problem. Okay, so assume if they're talking about daily that we're using 365 days. And also just a heads up in real life, sometimes when a bank says we're going to compound something daily, they actually round off the 365 and they just use 360 as their number. Okay, so just as a heads up, kind of have those different options for daily compounding. And then the last term there on that screen is crediting. So by process of elimination, which one is the crediting definition? Which one did we not use? Number 1, right? So it says it's interest that is compounded daily, but is paid either quarterly or semi-annually. So in other words, what they're basically saying is, we're going to calculate your interest for you daily. We're going to keep track of it for you on the computer, but we're not actually going to put that money into your account until the end of a quarter or the end of 6 months. So even though you're earning this extra money daily, it's not actually accessible to you until the end of the quarter or the end of the 6 months where they decide, okay, now we're going to put the money into your account for you. So they're crediting the amount to you. They're saying, yes, we owe you this. We know we owe you this. We're keeping track of it. We're just not actually going to put it in your account until the end of a quarter or the end of 6 months. Okay. One more screen of vocabulary, and the reason they're kind of split up into 2 sections here, because you can see there I've got another little summary screen. We're actually looking at 3, 4, and 3, 5 together today. We're mostly focusing on 3, 5 because 3, 4 is sort of this exploration of compound interest, and it's just tedious. Like, we already know some things about compound interest, so going through 3, 4 is just like, oh, for the love of heaven, get on with it. It would be a good lesson if students had never seen compound interest before, but you have. So we don't really need to do 3.4, but the first set of vocabulary, first 6 things that we just talked about, are actually from 3.4. And that's really probably the biggest thing that we're going to take from 3.4 is some vocabulary. But a few more things from 3.5 that we're also going to talk about today. The actual compound interest formula, which we'll look at in a little more specifics in just a minute. That's number 3. Hopefully everybody recognizes that, remembers that. And then this idea about annual percentage rate and annual percentage yield. They sound very similar, but they are quite different. The annual percentage rate is what you are told anytime you are told at what rate your money is going to grow. So when you are compounding it quarterly or daily or monthly or whatever it is you're doing, this is by how much it's going to grow with respect to a year. So if I tell you you're going to get 6% APR, that's your annual percentage rate that they're stating to you for a year's time. Now, if you end up compounding for more than one time within the year, you'd go quarterly, you'd go monthly, something like that, then you have to take that percentage rate and you have to divide it by the number of times you're going to compound so that you find out how much interest you actually get in that period of time. So if I'm going to do 6% as an annual percentage rate, but then I'm going to compound monthly, I don't get to take a full 6% every month, right? 6% is what you take for the year. So I have to take my 6%, divide it by 12, in order to find out that I would actually be getting about 0.5% every month. Okay? When you are given a percent in a compound interest formula, we assume that they're always giving us the annual percentage rate unless they tell us differently. So they're always giving us the APR value unless they specifically say differently that it's something else. Okay? Annual percentage yield is number 2 up there. So the annual percentage yield is the simple interest rate that would be required to give the same amount of interest as the compound interest did for 1 year. So let me say that again. An annual percentage yield is the simple interest rate that it would take for you to get the same amount of interest as you did with the compounding for 1 year. So what ends up happening is even though the problem may tell you that you're going to use 6% APR and you're going to compound monthly, if you actually compare the amount of money that you deposit and the amount of money that you end up with at the end of the year, it's going to end up being a little bit more than actual 6% of increase. Remember percent of increase problems way back from pre-algebra and algebra 1, right? So if you actually figured that out, the actual percent of increase that you get from what you start to what you end up with at the end of the year is actually a little bit more than 6%. And so what you're figuring out there, if you're trying to figure that out, is what we call the annual percentage yield. It's how much you actually ended up getting, how much more you actually got as a percent. Okay, we're going to take a look at how you find that and why that's important in a couple of minutes. But the big thing right now is just to understand the difference in the language. Annual percentage rate is usually the rate that they give you as part of the problem. And the annual percentage yield is usually something we have to figure out that is basically, if I took that same amount of interest that I got in 1 year of compound interest, but I did it in a simple interest problem, what would my rate be? Okay, that's what we're trying to find out. Question or?
I think it's kind of answered, but so for rates, basically how fast they give it to you.
Yeah, I mean they're going to quote you a particular rate at which your money's going to grow, right? Mm-hmm. And so when they say we're going to give you, if you deposit your money with us at Savings of America or whatever, we're going to give you 6% interest rate. Okay? So they're basically saying that over the year, let me put it this way. They're basically saying that if you were compounding annually, you would get 6%. Okay? It's an annual percentage rate. So if you were compounding annually, you would get 6% growth. Okay? But, as we've hopefully remember from problems in the past, the more often I compound, the more money I get. Not by a huge amount, but I get a little bit more if I compound quarterly rather than yearly. And I get a little bit more if I compound monthly rather than yearly or quarterly, right? So the more often I compound with everything else being the same, I can make a little bit more money. So because I can make a little bit more money by compounding more often, I actually end up making a little bit more than 6%. That's what the APY tells me, is how much do I actually make per year, as opposed to what you told me I should make if we had been compounding annually. And so it should always end up that as long as you're compounding more than once a year, you should always end up with an APY that's a little bit bigger than your APR. Okay, so you're always going to make a little bit more than what they actually told you.
Okay, that makes sense.
Okay? And we'll see how to figure that out in just a second.
Mrs. Gordon?
Yeah.
So when it comes to like the test, do you think we'll have vocab on it?
I will never give you vocab where I will put down APY, and then you have to regurgitate the definition. There may be questions where I give you phrases and I give you definitions, you got to match them up. Or there may be things where just because the problem is asking you for the APY, you just need to know what that means. Okay, so that sort of the vocabulary within the questions, you just need to understand what that means in terms of the question. But I'm never going to give you any questions where I put the word and you have to write out the whole definition. Okay, mostly you just have to recognize it and use it. Okay. All right, so the actual formula, hopefully this looks familiar. B equals P times the quantity 1 plus R over N, all raised to the NT power. So the B in this case represents your ending balance. If I put so much money into an account and I calculate everything out, this is how much is going to be in the account after a certain amount of time. We sometimes call that future amount or future balance as well. Those are all terms for the same thing. The P represents your principal. Principal is always your original amount, the amount you're starting with, the amount that you actually deposit to get things started. The R, again, is your interest rate. That's going to be the annual percentage rate that they tell you. Just remember, we always want to change it from percent form to decimal form when we put it in the actual formula to work it out. The N represents the number of times within a year that you're going to be compounding. So if we're compounding quarterly, we would use 4 for N because we're going to compound 4 times in 1 year. If we're going to compound monthly, then we use 12. If we're going to compound daily, we use 365. Okay? And then the T represents actual number of years that you're going to do this for. And so you can see here, we have to take the R divided by the N, because again, if they're giving us an annual percentage rate, we have to divide by N to see how much the rate is actually for each period of compounding, each month, each quarter, whatever. And up here in the exponent, we're taking N times T because we need our exponent to represent the total number of times we compounded. So if we're going to compound quarterly, 4 times a year, and we're going to do that for 5 years, how many total times are we compounding? 4 times a year for 5 years? How many times are we compounding? 20. It's the product of those two, right? So that's why this exponent is represented by that product of N times T. Because we need the total number of times we're going to compound in whatever time frame we're talking about. Okay, everybody familiar with that? Got it down? Kind of remember that from past classes? All right, so let's do a problem. So Nancy deposits $1,200 into an account that pays 3% interest, compounded monthly. What is her ending balance after just 1 year? So under these conditions, what amount would be in her account after 1 year? Round it to the nearest cent. All right, so in the formula, which variable are we going to try to solve for? The b, okay? So what number should I use for p?
1,200.
The 1,200. This is our investment. This is what we're putting into the account. Okay, so that's our p value. We always have 1 plus inside of the parentheses. Okay, the 1 is not something that's going to change. What is our R value going to be?
0.03.
0.03. We're going to take the 3% interest, change it into a decimal, and use 0.03 for R. But then we have to divide that by what? 12, because we're doing that yearly interest over 12 months, and we're going to compound every month. So in order to figure out what the rate for each month is, we're taking the 0.03 divided by 12. Okay? And then the 12 is also going to go up here as the end value. And what are we going to multiply by for t?
1.
A 1, because we're just interested in 1 year. Okay? And once you have that set up, grab the calculator. Like I said, this is a calculator semester, and definitely on these, use your calculator. There's really not any good way to even do this by hand. And it's ridiculous to ask you to take whatever 0.03 divided by 12 is, add that to 1, and then try to take that decimal to the 12th power by hand. Like, I wouldn't even do that. All right? So once you plug all of that in to your calculator, very carefully, making sure that everything's in its right place, how much money does she actually end up with?
1,236.50.
And remember, since we're talking about money, we need to make sure that we are writing our answer in a money form. And we are talking about US money because it's a US textbook. So we're almost always going to be talking about dollars and cents, which means you've got to round to the nearest hundredths place. I know some of you come from other cultures where money, going to the tenths place makes more sense, but it doesn't make sense in US money. So you've got to make sure you're giving me answers that are rounded to the nearest hundredths place when we're talking about dollars and cents. Okay, everybody agree with 1236.50?
Yeah.
Everybody okay with that? All right, now keep that in mind because now Nancy is getting mail. Whoa, where'd Nancy's mail go? Here we go. And she starts getting offers in the mail from other banks. Okay, so one bank says, hey, come deposit your money here with us. We'll pay you 2.78%, but we're going to compound it more often. So it's a little bit less percentage, but we're going to compound daily rather than just monthly. Another bank says, no, come deposit your money with us. We're going to pay you a little bit more at 3.25%, but we're only going to compound quarterly. And so the question is, are either one of those two offers any better than what Nancy already has going on? Okay, so to save a bit of time here, excuse me, I want, what do I want? You three girls, I want you to figure out what would happen with the 2.78. So use the same principle, do it for 1 year, but with 2.78% compounded daily. Okay. Boys, you're going to do the 3.25%. And you can join the girls. You can do the 2.78 also. I'll split up girls and boys for this one. So girls work on 2.78, boys work on 3.25. Same principle that she started with in the last problem, and still only going for 1 year. Question?
So for like the compounding daily, you say that they usually round it up to 360, right?
We're going to use 365. That was just more of a heads up that sometimes that does happen, but for us, we're going to use 365 whenever we're asked that.
Also for 1 year, right?
Yep.
Okay.
That way we can compare based on what she got, what she's getting currently. Oh, it's 4.
It's every 3 months. Yeah, it's every 3 months.
What did you get?
Yeah.
0.87. I got 0.36.
Wait, let me try.
Wait, can I type them from the phone
I got
So you guys good.
I got 0.36.
Yeah.
And 3.
I was looking at 86. I got less.
Yeah.
Yeah, 0.8.
Okay, everybody got an answer?
Yeah.
All right, so ladies, do you have a better offer for Nancy?
No.
No. How much did you get total?
1,233.83.
So 1233.83 compared to the 1236.50 she was getting before, so 2.78% out the window. Even though it's being compounded more often, the percentage is enough lower that compounding more often doesn't sort of balance that out. Okay? Boys, do you have a better offer?
Yes.
So how much did you end up with?
1,239.48 cents.
Okay, so 1239.48 compared to our 1236.50, that is a better offer. Okay, so it may seem like, well, yeah, duh, because that was the higher percentage, so of course that's going to be the better offer. But with the difference in compounding, that isn't always necessarily the case. This one happens to be enough higher that the fact that we're compounding less frequently didn't counteract that. The higher percentage rate really did give us a better return. But you cannot just assume based on percentages that the highest percentage is your best deal if your compounding is also different. Okay? So in this case, we needed to actually work these out, do each of them on a 1-year basis, and see which one is the better return. The 325 is the better return. Okay, makes sense? Questions so far? All right. Actually, which one do I like better? Yeah, let's do that one. So Kate deposits $2,350 in an account that earns a rate of 3.1% being compounded monthly. What is her ending balance going to be after 5 years? Round to the nearest cent. All right, so again, which of the variables are we going to solve for? B, we want the ending balance. Okay, what's my p-value going to be?
2350.
That's the amount we're depositing. Excuse me. 1 plus, what's my r value?
0.031.
0.031. And my n?
12.
Whoops, didn't change. Try again. There we go. 12. All right, and then what is my exponent going to be? How much?
60.
60, because we're going to take this 12, but this time we're going to multiply it by the number of years, which is 5 years. So we're going to end up with an exponent of 60. This is going to end up compounding 60 total times over the 5-year period. All right, so when we punch that into our calculators, how much is Kate going to end up with?
$2,743.45.
Everybody agree with that? 27.43.45? Yeah, look good? Look good? So, even though our 2 examples pretty much have been about finding ending balance, hopefully you again realize that with, what was it, 5 different with 5 different variables in this formula, as long as you're given the information for 4 of those, you should be able to find the 5th one. Okay, so it doesn't always have to be the ending balance we're trying to find. Maybe they're telling you that we want to end up with this amount. How much do I need to put in now to make that happen? Maybe they're telling you, I have this much right now. That's what I'm going to deposit. I want to end up with this much at the end of this much time. What's the percentage rate I need to get for that to happen? So then you'd have to solve for R. Okay. Most of your problems tonight are going to ask you to find B, but just kind of be heads up. Make sure you're reading carefully. Make sure that really is what the question's asking you for. Okay? All right. Let's talk about APY a little bit. So this example says that Sharon deposits $8,000 in a one-year CD at 3.2% interest, which is compounded daily. What is Sharon's annual percentage yield, APY, to the nearest hundredth of a percent? So going back again to what the definition said about annual percentage yield, we need to figure out what is the percentage rate in simple interest that would get us the same amount of interest as the compound interest did. Okay? So there's two ways we can do this. The first way is more of a kind of grunted out way. Okay? And it works and it's fine, and we'll go through and kind of show you how to do it that way. And as sort of a backup, definitely you could do it this way. But then I'm also going to show you a bit of a shortcut way that you could do it. Okay? And then you can pretty much choose after that. If you prefer more of the grunted out and just work it all out way, that's okay. If you can remember the shortcut way, it saves you a little bit of work. So the grunted out kind of way is to first decide how much interest do I earn in 1 year. It's all about what happens in 1 year's time. So how much interest do I earn in 1 year with the compounded interest? Okay, so my P in this case is what you deposit?
8,000.
The 8,000. What's my annual percentage rate?
0.032.
0.032. And how often are we going to compound?
Daily, so 365.
So it's going to be 365. And if I'm going to do this for 1 year, then what should my exponent be?
365.
Also 365. Okay, so go ahead and take a second and plug that in, see what you get.
Hey, Miss Gordon,
Mm-hmm.
did you say that that banks would round the year to 360?
Sometimes.
Okay.
But for our purposes, we're going to stick with 365. It
Okay.
was just more of a heads up that in
Oh.
real life, sometimes banks round it to 360 instead of 365.
Okay. All right.
They think they got it?
8,683.47.
8,683. Agree or disagree? Like it? Yeah? Everybody likes it?
Mhm.
We're good?
I was a little different.
What'd you get?
260.13.
8,200. What was the rest of it? 8,200 what? 60.13. All right, everybody punch the buttons one more time. Double check. Which one should it be?
Yeah, I got 8,260.
that's a
Yes, this is a
sorry.
3. You're the one who read it to me.
Yeah, I read it too.
3.2%, so it's 0.032.
Wow. Okay. Yeah, I checked.
Yeah, 8,260.13.
Okay, so that's the one we like. All right, so let's erase this one. Ooh, that's a big eraser. Actually, I'm just going to erase the whole thing and rewrite it. All right, so $8,260.13. We're all happy with that now?
Yeah.
Okay, now, here's one of the differences between compound interest formula and simple interest formula. When we use the I equals PRT for simple interest, what we find is interest. And we have to add interest to our principal to get what's in the account. Compound interest formula is opposite. What we find is the new amount in the account. And in order to find interest, we then have to figure it out. So we now actually have to subtract the $8,000, which was Sharon's money. That's what she deposited in the first place. We subtract that $8,000 right here in order to figure out how much interest she actually earned. Okay, so simple interest formula finds interest for us, and then we have to add it to get the account balance. Compound interest formula finds the account balance for us, and then we have to do the subtraction to figure out the actual interest. Okay, everybody clear on that? So in this case, she earned $260.13 in interest. Now we put that into the simple interest formula. Whoops, got my 13 there. So now in the simple interest formula, we've got $260.13 for interest. We're still going to use the $8,000 for the deposit for the principal. The R is what we're trying to find. And then what's my time going to be? 1, because we're just doing this for 1 year. So what that ultimately means is that in order to find this rate for simple interest that would produce the same amount of interest as my compound interest did, I just need to take 260.13 and divide by 8,000. And what does that end up giving us?
Wait.
It's 0.025,
0.0325.
which as a percent is 3.25%. So that simple interest rate that you just solved for, that is the annual percentage yield. That is the APY number that we're looking for. And as you can see, it's just a tiny bit bigger than the 3.2% interest we were told in the first place. Excuse me. Okay? So that's one way to figure it out. Basically, it takes 3 steps. The first step is to find the compound, to use the compound interest formula to find your new amount. Second step is to subtract your principal to find out how much actual interest you earned. And then the third step is to plug that into your simple interest formula and solve for R. Okay? Excuse me. So very doable. But I think you can see that if we needed to do this very often, it would get a little bit tedious to have to go through these 3 steps every time. So let's see if we can come up with a bit of a shortcut. So let's look at it just in terms of the formulas for a second. And kind of what we just did in that problem, but in formula form with all the variables. So we took and found the compound interest first, right? Used our formula, found compound interest. And then what did we do to find actual interest earned, the amount of interest? Once we found the compound interest, what was our next step?
Subtract the original amount.
Subtract the original amount, which is the P. Okay, that's what gave us the actual interest that was earned on that amount of money. Well, that interest then became the interest in our simple interest formula. So the interest that I get here has to be equal to the PRT in simple interest here. So I'm going to make this equal to the simple interest formula, PRT. Now, at first glance, you might be thinking, Mrs. Gordon, you're crazy. This does not look like a shortcut. This doesn't look like you're making stuff easier. But hang with me for a second. On the left side here, I have these 2 terms that are being subtracted. What do those 2 terms have in common?
P.
A P, which means I can factor that out. So if I bring P out, and then, all right, what's left? Here we go. 1 plus the R over N raised to the NT power. That's what's left from this term. What's left from this term? 1. A 1. Now, why does that help to factor that P out?
So you can then divide by it.
Yeah, by factoring P out and making it a factor out in front of everything, that means I can now divide both sides by it, which makes it cancel out on both sides. So what that actually tells me is, in order to find annual percentage yield, it really doesn't matter what amount I'm using for the principal. Okay? So what I'm left with now is this go back to black here. It'll work. There we go. 1 plus R over N raised to the NT power minus 1 equals RT. Well, what is my T value? 1, right? Because this is all in terms of what happens over the course of 1 year. So if I replace this T with a 1 and replace this T with a 1, then that means I'm down to 1 plus R over N to the N power, because N times 1 is just going to be N, minus 1 is going to equal just R. Now this is the R from simple interest. This one is the R for compound interest. But I have now simplified this down to a formula that becomes equal to the simple interest R, which is what the APY is. It's whatever the R from simple interest would have to be that makes all of this true. So, the shortcut is to remember that formula. If you can remember that APY, annual percentage yield, is really just the 1 plus R over N taken to the nth power, which is how many times we would compound in 1 year time, and then subtract the 1 from it, that's going to get you the APY rate that we're looking for. So if you're someone who is pretty good at memorizing those kinds of things, this makes the problem a whole lot easier. Because now substituting into that is a fairly easy thing to do, and again, you just go to your calculator to actually work it out. If you're someone who's not so great at the memorizing thing, then you just need to kind of remember what the 3-step process is. Find out your new balance with the compound interest formula, subtract the principal to get the actual interest, and then put that into your simple interest formula to find the rate. Either way works. Either way is going to get you an answer. It's just a matter of whether you want to memorize or not, how many steps you want to do. And just to show you this really does work, in our problem we said we had a rate of 0.032, correct? Is that right? 3.2%. We were compounding daily, so 365 for n. Put 365 up here, subtract 1 from the whole thing. What do we get? Let's that into your calculator quick. Which as a percent is 3.25%. Exactly the same answer we got the other way. Okay, so either way is going to work. You just have to decide which way you're more comfortable with and which way you're going to have a more likelihood of getting the correct answer. Okay, so let's give you a chance to try one on your own. Barbara deposits $3,000 in a 1-year CD at 4.1% interest compounded daily. What is the APY for her situation rounded to the nearest hundredths? No, sorry. Yeah, nearest hundredth of a percent. So I want to end up with the nearest hundredth of a percent as our answer. Everybody got it? do you think? 4.19? 4.19? 4.19?
I think I did
See what they say. Ooh, 4.18. The difference is that I think you end up with 4.195. If I remember correctly. Does that sound right?
4.185.
Okay, 4.185, excuse me. 5 is one of those that can kind of go either way. Generally, rounding rule says if it's 5 or above, you round up, unless you're a bank. Generally, if the bank is paying you and the next digit is a 5, they round down. If you're paying the bank and the next digit is a 5, they'll round up. So the bank will do whatever is more beneficial to them when the next digit is a 5. So when it comes to paying you, they'll round down. When it comes to you paying them, they'll round up. Most other numbers, they'll round normally, but 5 is one of those that they'll kind of mess around with. So 4.18, 4.19. Again, this would be one of those where as long as you had the work, you showed what you were dividing out or what you were working out to get that answer, you'd be fine. Okay? All right, so now that we know how to figure the APY, what's it used for? Why is it helpful to us to know how to find APY? Well, because APY takes what could be going on with compounding and basically translates it into simple, it allows us to make comparisons. And to make comparisons that actually are like comparing apples to apples. And so as an example of this, let's go back to Nancy here for a second. Where'd Nancy go? Here's Nancy. So remember Nancy with her different offers in the mail, trying to decide if any of the offers was better than what she already had? To just look at the percentage rates is tough because the compounding is different. Sorry guys, my throat is really cruddy right now. But if she could find the APY for each of her 3 situations, then compounding the percentage rates would be a real, true comparison. The higher percentage rate really would give her the better deal. The lower percentage rate really would be the crappiest deal out of the 3. Okay? So when you're talking about percentage rates in compounding, and especially when the compounding is all different, it's kind of like trying to compare apples to oranges to bananas. But when you change them to APYs, now you're comparing watermelons to watermelons to watermelons. Okay? So let's just do that really quick as our final example. Let's go back to Nancy. Let's figure out the APY for all 3 of her situations, just to see what kind of numbers would come up and to see how the comparison still ends up, I hope, supporting what we said before. So again, we're going to split this up. Morgan and Michaela, I want you guys to figure out the APY for this situation. So her original situation of $1,200, 3% interest, compounded monthly. Got it? 1,200, 3% monthly. All right. Gentlemen, you get to do the 278 this time. Okay, so you 3 figure out what the APY would be for the 2.78% compounded daily offer.
What was the original amount?
1,200. And ladies, you get to figure out the 325 offer. What would be the APY for 3.25% compounded quarterly? $1,200.
Wait, I'm sorry, so this is like over 1 year or 4 years?
APY is always over 1 year.
Okay.
Okay, you're always comparing for 1 year. Okay, everybody got APY numbers? All right, so again, just for the shortcut, if we were using the formula for APY, in the first situation, which was the original situation of 3% compounded monthly, we'd have the 0.03 here for R, we'd have the 12 there for N, and we'd have the 12 there for N. Okay, and what did you guys end up with for APY? 3.04%. Okay. The second situation with 2.78%, so that's going to be 0.0278. Compounded daily, so N is going to be 365, which means 365 is also going to be our exponent. And what did you guys end up with? 2.8? 81%. Okay. And then our other offer with 3.25%, so 0.0325 for R. That's compounded quarterly, so 4 for our N's, both in the denominator and the exponent. And what did you get for an APY? 3.29. So now you can use these three percentages, these APY percentages, to make an actual comparison. And you can still see that the 3.29 is the better return, so that's still the better offer. Okay? So that's actually where APY is used, is to be able to make comparisons among different kinds of compounding situations where both interest and the amount or the frequency of compounding is different. By changing it to APYs, then it's kind of putting it all on the same playing field, and then you can make reasonable comparisons. Okay? Questions? Make sense? All right, so your assignment, I think there's 8 problems it's just from the lesson 3.5. If you want to take a look at 3.4, you can, but I think we pretty much covered what we need from there. So it's just on lesson 3.5. 8 problems will be due for Thursday. Okay? And then Thursday I'll get your quizzes back to you as well. Okay? All right, you can get packed up if you like. Just hang on until the bell rings, please.